Alright, so in this video we're gonna go over an chips and cheese article. Um, I don't understand a lot from these articles. I'm just like slowly picking up on the buzzwords pipeline. I don't know, generating address units, ALU, FMA, reorder buffering, and Malmont. Did I say that right? I don't know. What else? And let's just go over this one that we went over, just to remember what we did. The in order, out of order execution. Right. We remembered that part. Reordering buffer, and yup. Register files, out of order, retire. Yeah, so we read this article. I wanted to start reading this, and we're gonna see how much of it we can understand. I might do this in 2 videos because I'm not sure how much of it I can do in this one, but yeah. So Clam Chowder wrote this. I don't know what the anonymous who wrote these, but like these are good articles if you want to pick up some chips knowledge, you know. So yeah, I'm for the next videos I'm going for Sam Ziloff blogs too. These are for future. His blogs are down, but maybe I can find it in the archive website where they archive your website, and it's like basically a snapshot. We can do it from there. Yeah, that's a good idea for next video. And then probably after that, I'm going to go back to LLVM compilation and stuff like that. So let's start. Alrighty. So Nvidia and AMD. Okay, Grasshopper, Nvidia's half-8 APU. So that's probably either accelerated processing unit or AI processing. Either of those two. Nvidia and AMD are the biggest players in the high-performance GPU space. But while Nvidia has a huge GPU market share advantage over AMD, the latter's CPU prowess make it a strong competitor. AMD can sell both a CPU and a GPU as one unit, and that capability has gotten the company wins in consoles and supercomputers. Oak Ridge National Laboratory's Frontier supercomputer is one such example. Their AMD MI250X GPU's interface with a custom EPYC server CPU via Infinity Fabric. Of course, Nvidia is not blind to this situation. They too have a high-speed in-house interconnect called NVLink. Nvidia has also dabbled with bundling CPUs along their GPUs. The Nintendo Switch's Tegra X1 is a prominent example, but Tegra used relatively small CPUs and GPUs to target low-power mobile applications. Grace Hopper is an attempt to get Nvidia's CPU efforts into high-performance territory. Beyond providing server-level CPU core counts and memory bandwidth, Grace Hopper comes with Nvidia's top-of-the-line H100 data center GPU. Alright, so Grace Hopper 200 rendering from Nvidia showing the CPU on the left and GPU on the right. I'll be looking at GH200 as hosted on Hydra. Let's see what this is. Hydra host. Alright, so an hour cost $3 on H100. That's not a joke. It's not a joke. But that's what it is. Okay. The one I'm looking at has 480 gigabyte of LPDDR5X memory on the CPU side and 96 gigabyte of HBM3 on the GPU side. I've already covered Neoverse V2 in Graviton 4, so I'll focus on implementation differences rather than going over the core architecture again. System architecture. GH200 bundles the CPU and GPU together. The Grace CPU consists of 72 Neoverse V2 cores running at up to 3.44 GHz, supported by 114 megabyte of L3 cache. Cores and L3 cache sit on top of Nvidia's scalable coherency fabric. SCF is a mesh interconnect with cores and L3 cache slices attached to mesh stops. So as you can see, there's 72 cores and 72 cores ARM Neoverse V2 cores with 2x perf/w over today's server, and then there's 170 megabyte. That's your L3 cache, and your NVLink provides you with 900 gigabyte of transfer per second, and then Nvidia scalable coherency fabric gives you 3.2 terabyte per second, and then your LPDDR-SX, that's your memory, gives you a 500 gigabyte per second. And SCF is scalable coherency fabric. Scalable coherency fabric's responsibilities include ensuring cache coherency and proper memory ordering. From a core-to-core latency test, those requirements are satisfied with reasonably consistency latency across the mesh. Latency is generally comparable to Graviton 4's, which uses ARM's CMN700 mesh interconnect. DRAM access is handled by a 480-bit LPDDR5X-6400 setup, which provides 480 GB of capacity and 384 GB per second theoretical bandwidth. Graviton 4 opts for a 768-bit DDR5 5200 setup for 500 GB per second of theoretical bandwidth and 768 GB of capacity. Nvidia may be betting on LPDDR5X providing lower power consumption, as DRAM power can count for a significant part of a server's power budget. Okay, so I need to figure out what this is. Alright, so Samsung makes these. Built to power, what's next? Pioneering premium low power DRAM with speeds up to 1.25 faster and 25% better power efficiency compared to the previous generation. Premium low power DRAM LPDDR5X is transcending mobile devices. It leads the power DRAM market, empowering high performance from PCs, servers, vehicles to emerging to on-device AI application in groundbreaking ways. So, premium power saving. Okay, so these are their technical analysis, and there's quite different models. Not sure what this is, but it can go up and down. So we have, for comparing these, we have the density, which is probably how much memory per centimeter square, maybe. And then it's in 64, so it's integer 8 bytes. The speed is 7 7500 megabit per second. Why is it megabit per second? Why is it not megabyte? Alright, voltage is 1.8, 1.05, 1.05, 0.9, 0.5, and then the package is FPGA. And then these are all either mass production or samples. Interesting. Alright, so what is a FPGA package? Fine pitch ball grid array is a laminate substrate based chip scale package with plastic overmolded encapsulation and an array of fine pitch soldered ball terminals. Okay, so that's what how the thing goes. How the chip is designed to connect to the board, I guess. To whatever the board is. Alright, sure. Providing lower power consumption as DRAM power can count for a significant part of a server power budget. GH200's H100 GPU sits next to the Grace CPU, even though both are sold as a single unit. It's not an integrated GPU setup because the two chips have separate memory pools. Opting against an integrated GPU is a sensible decision because CPUs and GPUs have different memory subsystem requirements. CPUs are sensitive to memory latency and want a lot of DRAM capacity. GPUs require higher memory bandwidth but are less latency sensitive. A memory setup that excels in all of those areas will be very costly. GH200 avoids trying to square the circle, and its H100 GPU comes with 96 GB of dedicated HBM3 memory. That's good for 4 TB per second of theoretical bandwidth, for more than what the LPDDR. 4 TB of theoretical bandwidth per second. Oh my god. Okay, 8th gen Intel Core is this an app? Is it an ad? No. With Radeon RX Vega M. So you have your 4 GB of high bandwidth memory Gen 2. You have your custom Radeon RX Vega M graphics. You have your 8th generation Intel Core 8 series processor. You have your Kaby Lake processor. It's 4 core, 8 thread. I always thought the number of thread you can have is the number of cores, but today I was proven wrong. 3.1 gigahertz base cycle, turbo up to 4.2 gigahertz. 8 megabyte cache with 2 channels, DDR4 2400, Intel HD graphics 630, 24 EUs up to 1100 megahertz, overclocking software kit available, Radeon RX Vega M graphics, GLSQ software kit. Is it SQ software kit unit? What does SQ? Stock keeping unit. Yes, I worked at a retail. I should have known this. Yes. That's SDK, software development kit, right? software keeping unit, right? Stock keeping unit. Okay. Then you have GL software keeping unit 65W watts package DDP 20 compute units base slash boost clock 931 slash 1011 megahertz 2.6 teraflops, and you have ROP 32 pix per CLK GHSK stock keeping unit 100 watts package DDP 24 compute units base over boost clock is 1063 over 1190 megahertz 3.7 teraflops, and that's that. Okay, so is this the CPU that's on there? I'm not sure. Maybe. Not sure. Oh no. Alright, let's continue. We'll probably figure it out by the end of the article. Conceptually, GH200's design is similar to Intel's Kaby Lake CPU with AMD's Radeon RX Vega M graphics. That design also packages the CPU and GPU together as one unit. A 4GB pool of HBM2 memory gives the GPU high memory bandwidth, while regular DDR4 memory gives the CPU high memory capacity and low latency. GH200 of course does this on a much larger scale on both the CPU and GPU side. So you have your high speed I/O, you have 4 connections, 16 peripheral communication interconnect. Oh god. Yes, if I remember correctly. And then you have your NVLink that goes from your gray CPU to Hopper GPU. And then you have your LPDDR5, 500 of RAM. And then you have your high bandwidth memory, which is 96. It's less than 96 gigabyte of RAM. And then you have an NVLink that can connect to 250 up to 256 GPUs, and the speed is 900 gigabytes per second. Wow. You can have 18 NVLink to each one of these guys. That is crazy. That is crazy. But an integrated GPU design has benefits too, mainly allowing for faster communication between the CPU and GPU. Games don't require much bandwidth between the CPU and GPU as long as there is enough VRAM to handle the game in question. But computer applications are different and can involve frequent data exchange between the CPU and GPU. Therefore, Nvidia connects two dies with a high bandwidth proprietary interconnect called NVLink C2C. CPU chip to chip, I guess. NVLink chip to chip offer 900 GB per second of cross-die bandwidth or 450 GB per second in each direction. That's an order of magnitude faster than PCIe Gen 5 X16 link. Besides higher bandwidth, NVLink C2C has hardware coherency support. The CPU can access HBM3 memory without explicitly copying it to LPDDR5X first, and the underlying hardware can ensure correct memory ordering without special barriers. Nvidia is confident enough in their NVLink C2C implementation that HBM3 memory is directly exposed to the CPU side as and NUMA node. Alright, local versus remote NUMA memory bandwidth. AWS Graviton, remote, and then local. And then you have your bandwidth. It goes gigabyte per second, and your AWS Graviton for what is AWS Graviton for? Graviton for is a family of processor designed to deliver the best price performance for your cloud workloads running in Amazon Elastic. So EC, yeah, Elastic Computing. Interesting. This is the chip. Oh, it's Cortex A72. ARM designed this. This is, oh, ARM is going crazy. ARM is going crazy. Let's just look at this. Ooh. Oh, I mean, they only went public after the COVID, but good for them. Good for them. Good for them. I guess we'll see what happens. So, and then you have your AMD EPYC 9V33X NPS to read, and then you move from that to Nvidia GH200 and the AMD EPYC 9754, and then all of that. And then you go to accessing the HBM3 memory pool across NVLink. C2C provides comparable bandwidth to AMD's current generation Zen 4 servers in a dual socket configuration. It's a good performance, if a bit short compared to the theoretical figures. Bandwidth is still significantly higher than what AWS can achieve between two Graviton 4 chips, and shows the value of Nvidia's proprietary interconnect. Bandwidth from Grace's local LPDDR5X pool is also solid, and on par with AMD's Bergamo with DDR5-4800 with that. Latency, however, is poor at nearly 800 nanoseconds, even when using 2 megabyte pages to minimize address translation penalties. That's a difference of 592 nanoseconds compared to accessing the directly attached LPDDR5X, which itself doesn't offer particularly good latency. Alright, so CC is for cross chip probably. Oh no, C2C is probably to chip to chip, but cross chip memory latency is cross socket penalty, remote DRAM latency, local DRAM, and apparently the latency is higher on Nvidia GH200. Part of this is undoubtedly because HBM is a technology designed to offer good latency characteristics. But testing from the H100 GPU shows about 300 nanoseconds of DRAM latency, suggesting HBM3 latency is only a minor factor. NVLink C2C therefore appears to have much higher latency than AMD's Infinity Fabric or whatever Graviton is using. Intel's QPI also offers better latency. What is Infinity Fabric? Show me this. Alright, so it's, I guess, proof of concept right now. Sure for right now. To make things worse, the system became unresponsive during that latency test run. The first signs of trouble appeared when VI A simple text editor took more than several seconds to load. Even weak systems like a Cortex A73 CBSC usually load Vim. That's Vim, right? Yeah, I believe so. Instant. Then the system stopped responding to all keystrokes over SSH. When I tried to establish another SSH session, it probably got past the TCP handshake stage because it didn't time out, but the shell never loaded, and the system remained unusable. I eventually managed to recover it by initiating a reboot through the cloud provider, but that sort of behavior is non-ideal. Since GH200 is a discrete GPU, it's insightful to compare link latency against other discrete GPU setups. Here I'm using Nemesis Vulkan uplink latency test, which uses VK map memory to map a portion of GPU VRAM into the test program's address space. Latency is then measured using pointer chasing addresses, just like above. So VRAM access latency from CPU side is lower for Nvidia compared to AMD Ryzen 5950X plus AMD Radeon RX 5700, and then Intel Core i7 4770 plus Nvidia GTX 1080, and then AMD Ryzen 4800HS plus Nvidia RTX 2060. Alright, that kind of, it's good for Nvidia, I guess. This comparison is more reasonable, and NVLink C2C offers better latency than some discrete GPU configurations. It lands right between setups with AMD's RX 5700 XT and HT 7950 latency. With that in mind is quite reasonable. However, CPU code will need to be careful about treating HBM3 memory simply as another NUMA node because of its high latency. A CPU general Neoverse v2 implementation. A CPU core architecture's performance can vary depending on implementation. Zen 4, for example, behaves very differently depending on whether it's in server, desktop, or mobile CPU. Neoverse v2's situation is no different. You can vary even more because ARM wants to give implementers as much flexibility as possible. So on Nvidia Grace, you have your clock speed going up to 3.44 gigahertz. On Graviton, it's around 2.7, 2.8, and ARM Neoverse v2 emulation environments around, it's 3 gigahertz. And then core count on Nvidia Grace goes up to 72. Amazon Graviton has 96 cores, and then ARM Neoverse has 32 cores. And then you have 1 megabyte of L2 cache, 2 on the others. And your interconnect is Nvidia SCF. And on Amazon it's ARM CMN 700. And you have L3 cache, you have 114 megabyte. On Amazon you have 36 megabyte. On Neoverse you have 32 megabyte. And then your main memory is 480 gigabyte of DDR5, and then for Amazon Graviton you have 768 gigabyte of LDDR5 2, but the bus is larger on this one. This one has 768 bit bus, the other one has 480 bit bus, and then ARM Neoverse has 128 bit bus. SCF is SCF. What is Nvidia SCF? It's your scalable coherency fabric. Scalable coherency fabric. Scalable coherency fabric. Yes. All right. Grace targets parallel compute applications. To that end, Nvidia opted for a large shared L3 cache and higher clock speeds. Less parallel parts of a workload can benefit from a flexible boost policy, giving individual threads more performance when power and thermal conditions allow. A large L3 might handle better when threads from the same process share data. Graviton 4, on the other hand, has to serve a lot of customers while maintaining consistent performance. Neoverse V2 cores on Graviton 4 get a larger L2, helping reduce noisy neighbor effects. Low clock speeds minimize workload-dependent thermal or power throttling. Finally, a high core count lets Amazon fit more of their smallest instances on a single server. A latency test shows the memory hierarchy differences well. So cache and memory latency 2 megabyte pages. The test size goes up, and then you have your latency per counted number of cycles. And Graviton is kind of here, and then AMD, it's over here, and then Nvidia is kind of higher than all of them, but I guess he said in the same article that latency is not that big of a deal for GPUs. I'm not I don't remember correctly if he's I don't have enough information about the system, but he said that the latency doesn't matter, the high bandwidth to GPU matters. But ouch. For CPU, your latency matters. So there's that. Alright. Higher clock speeds do hand Grace an advantage over Graviton 4 when accesses hit L1 or L2, but L3 latency is still sky high at over 38 nanosecond. Even Intel Sapphire Rapids, which also accesses a giant L3 over a giant mesh, does it slightly better with 33 nanoseconds of latency. L3 cache misses head to Grace's LPDDR5X controllers. Latency at this point is over 200 nanosecond. Graviton 4's DDR5 is better at 114.08 nanosecond, putting it in the same ballpark as other server CPUs. And then we go over the bandwidth. Like it's fine if we cover the rest. Alright, so what we learned. Nvidia is making this Grace Hopper H200, and then they have your NVLink. They have their high bandwidth. Apparently the CPU that's on this thing, it's slower, it has higher latency compared to Graviton 4, which is for Amazon, and it was designed by ARM. There's that. The memory they are using is DDR5s. It's not LP for other guys. ARM, Neoverse, V2 emulation, all of that. So there's that for right now. I'm going to record the second part of this video soon, probably tonight. So thanks for watching this one, but keep looking forward for the second part.